Alrighty, so let's take a few notes here on Newton's laws. You've written down sort of what the internet says about them. Let's just try and sort of fill in some blanks here a little bit, kind of, okay? Okay, so a force is a physical quantity that can affect the motion of an object. Since a force has magnitude, direction, and a point of application, it is a vector quantity. Now, do you need to write all that down? All you need to write down is forces are vectors. That's all you need, isn't it? Isaac Newton was the first person to clearly describe the relationship between force, mass, and motion. Newton's laws of motion not only apply on Earth, but are true throughout the universe. And we use this word to describe them. Universal. They are true everywhere. Now, there's a little bit of a legal disclaimer to that, because that's not entirely true. There are certain situations where Newton's laws don't appear to apply. Let's put it that way. I'll just.
Like in what is it actually a law? Or
It's in certain situations Newton's laws don't apply because of the motion of other objects, right? So it's I'm not going to talk too much about it today. We'll get to it. We'll get to it. Okay, but generally Newton's laws are pretty much true for everywhere. Okay. Before we get talking about Newton's laws, we got to talk about different types of forces. Yesterday I gave you the fundamental forces. Anybody remember what they are?
Yep.
Give me the easy one first.
Yeah.
Gravity. Strong nuclear. Weak nuclear. Electromagnetic. Did you like my weak? Okay, these are not fundamental. These are just common everyday kind of ones, okay, that you might encounter. Buoyant force. When you go swimming, right, or even if you're in a boat, the buoyant force is what holds you up. Buoyant force.
Would that be gases too?
Yeah. When would a buoyant force act sideways? Remind me a little bit later to talk to you about the helium balloon in the car thing.
Is it gravity? Because gravity is pushing everything else down, which would, like, it's pushing the air down.
Yeah.
There's a helium balloon in the air, then the air is heavier, so it goes underneath.
Yeah, it has to do with the density of helium. Yeah.
But it's the gravity that's the force.
Gravity's pulling down, but the helium balloon is also pulling the Earth up. It's just that the helium balloon is so tiny and the force is zero, basically, right? Ian needs to put his phone away. There's elastic force that's produced by stretching, compressing, or twisting an object. Like if I take the elastic band that was around these cards and I stretch it, right, there's a force there, right? You compress something, like, maybe a tennis ball or a spring or something other, you compress it, there's an elastic force trying to push out, right? So there's an elastic force. These are all just basically, for your purposes, forces are forces, and it doesn't really matter what causes them. Forces are forces. The electrical force produced by the interaction between charged particles, that some could argue is the fundamental force, electromagnetic, right? Again, positive and negatives attract, positives and positives repel, right? Frictional force. Now, friction occurs like just about everywhere, right? Produced from one surface, moves over another. It always acts in a direction resisting motion. Does there have to be motion for there to be friction? Like when I slid the book across the table, we all know that it was friction that caused it to slow down, right? Does there have to be motion for there to be friction? Does there have to be motion for there to be friction? Or does friction only occur when something's moving? Ben, what do you think? Yeah, what? There has to be motion? Okay, so you would agree that when I slide the book across the table, there's friction that slows it down, right? Would you agree that if this was a frictionless surface and I lifted this end, that the book would slide down? Does the book slide down? Therefore, there must be friction. In fact, it's friction that causes it to not move, isn't it, right? Is there a force kind of down the ramp, down the table? Like if I put a Hot Wheels car or a marble on here, JZ, can you catch this for me? The marble is going to roll down in the ground, is it not? Right?
No, there is friction.
If I do this, well, there's not enough friction for the. Yes, you can. If I do that, there's not enough friction to contain the marble, but there's enough friction to hold the book in place. So yeah, there doesn't have to be motion for there to be friction. Gravitational force produced by the attraction of any two objects, it acts downward on Earth, right? But any two objects. We talked about yesterday about just how attractive the filing cabinet was.
Yep.
You want to play a little game with me here, Nick?
Okay.
Who's more attracted to the filing cabinet, me or Nick?
I don't know. You're closer.
Me, because I'm closer. Yeah. In fact, you're about like 3 times as far away. He'd be about like 1/9 as attractive. Sorry. Yeah. Magnetic force produced by the interaction of at least one magnet and another object. Are 2 magnets attracted to each other? Are 2 magnets attracted to each other? How come you listen to the music, Brian? If they're opposite poles, right? If they're opposite poles, they would be attracted to each other. If they're not opposite poles, they would repel each other, right? One magnet, though, like, this kind of thing, will be attracted to metal, right? So magnetic force as well. Okay, common forces. Is there one more? There might be. No, there isn't. Okay. Here's Newton's first law. You know that music's still playing, right? Here's Newton's first law. It says, if there's no force acting on a body, it will continue in its state of rest, or will continue moving along a straight line with uniform speed. Is that pretty close to what you said, Alex?
Yeah.
Pretty close. What's different about this one from the one you said? There's one thing that comes to mind, I think. When you read what you wrote down, can you read it first? What did you write down just before? Or do you have it? What did you write down?
An object at rest stays at rest, and an object in motion stays in motion, with the same speed and direction unless acted upon by an unbalanced.
Okay, no, I'm wrong. You did say it. I apologize. I thought maybe that he didn't have, because most people say that Newton's first law says an object at rest stays at rest, or an object in motion stays in motion. And they usually leave it at that, right? Once you sort of get to your guy's level, then you need to say that it will continue moving along a straight line with uniform speed, or the same speed. In other words, it'll keep moving forever, same direction, same speed. How come that doesn't work on Earth? The big bully friction. Right? The big bully friction. But if I could make it frictionless, the book would continue until it gets to the edge of the table at a constant speed in a straight line. What would happen when it got to the edge of the table? It's going to fall. How come? There's gravity now in play, right? If there's no gravity, what would it keep doing? Straight line, same speed, constant. Okay? When I say no force, what I really mean is the net force is 0. Because if I'm driving in my car at 100 kilometers an hour down the road, I'm clearly traveling at a uniform speed and in a straight line. But there's friction, so how can I be moving in a straight line at uniform speed if there is friction? There's also what? The engine in my car that's doing what? Producing a force, right? So in other words, if I draw a little diagram here, I've got an applied force and I've got a friction force. And if you add those up and they balance each other off, then that means you have a net force is 0, right? So it's the net force that matters. There can be lots of forces. It's the net force that matters. This is also known as the law of inertia. The law of inertia. Things like to keep on doing what they're doing. It's a teenager law. Teenagers don't like change, right? They like to keep doing what they're doing. If they're sleeping, they like to keep sleeping. If they're texting, they like to keep texting. If they're doing homework, maybe not. Maybe not so much. See, I told you Newton's laws aren't always true. Okay, my friends, here's your first quiz. I'm not counting marks, I'm not doing anything, but I'm going to ask you the question. And I will ask you this question many, many times in the next 2 or 3 weeks. I will ask it many different ways. Is this object moving? I'll give you about 10 seconds to come up with an answer, and then I want to show of hands. I'm going to ask yes, it is moving, and I'm going to want people to indicate no, it's not moving. Is this object moving? Who says yes, it's moving? Brett is the lone wolf. Good for him. Oh no, a couple more here. Okay, who says no, it is not moving? Who didn't vote? Rat out your friend. Who didn't vote? I'm going to try one more time. Yes, it's moving. Got 3. No, it's not moving. None of you are right. How can that be? How can none of you be right in a yes/no question?
Maybe.
Well, it's because the answer is maybe. The answer is maybe. It depends. What does it depend on? It's kind of a circular argument. It depends on what it was already doing.
Well, how are we supposed to?
You don't. You don't know. It was an impossible question to answer. So it's okay if you got it wrong, because I guaranteed you to be wrong, because I didn't put the possible answer up there. It's like a multiple choice question where the answer's not there. It depends, but I got your attention, didn't I? It depends on what it was doing. Because if it was a rest, like if I push on the filing cabinet with 50 newtons, and 50 newtons isn't enough because of friction, does the filing cabinet move? Nope. Doesn't move. But if the filing cabinet was already moving, and I pushed with 50 newtons, and 50 newtons back from 8, what's the filing cabinet do? Keep right on moving at a constant speed and a constant friction. So it depends on what it was doing. Go ahead. No, come on.
So is that going to be like the already the force that was already on it? Is that going to be in the question?
Yeah. Don't worry. You'll have lots of chances to re-answer that question. Newton's second law. This is a big one. Marissa needs to put her phone away for this one. That's how important it is. Okay? The effect of an applied force is to cause the body to accelerate in the direction of the force. The acceleration is in direct proportion to the force and in inverse proportion to the mass of the body. I think I'm going to have to do this. I'm going to have to do this. It's not letting me. What does that mean? Ian, what does that mean? It's English.
If you, whatever force you push on it, it's going to accelerate
In that direction, exactly, right? Like if the book is sitting here and I give it a push towards Dylan, it's going to accelerate towards Dylan. It's not rocket science, unless you're dealing with rock. Right? No big deal. The acceleration is direct proportion to force. If I push hard, catch Dylan.
Good catch.
He had no chance of catching that.
Yeah, you did.
No, he didn't. He was trying to catch it above the table. It was impossible.
He's got it for 3
It was never going to stay above the table. If I push really hard, the acceleration is really fast. If I push really small, it's really small. Right? And it's an indirect proportion to the mass of the body. If I push really hard on the book and it goes flying towards Dylan, that's great. But if I push the same thing with the filing cabinet, it doesn't go towards Dylan. It doesn't go very hard at all. How come?
You didn't push it towards Dylan.
Well, I didn't push towards Dylan, but if I did, it's like, what, maybe 1/500th of the mass, depending on how full it is? So what does direct proportion mean? It means bigger force, bigger acceleration. Inverse proportion means bigger mass, less acceleration. That's what it means. And the mathematicians like to write it this way. In other words, the more force, the more acceleration, and the more mass, the less acceleration. And the mathematicians love this statement. A funny-looking thing, F over M.
What's the final thing?
Oh, every kid always asks me that. What's the funny-looking thing mean?
Looks like squid.
Some people say the fish, yeah, the fish thing. No, that one's not theta. That one is...
That's the same, that's pretty much exactly the same.
No.
Yeah, cool.
Can't remember my Greek letters. Alpha, beta, gamma. I don't remember. I'll have to look it up. It means proportional to. The fish thing means proportional to. It means, it's just a mathematical way of saying bigger F means bigger A. Bigger M, because it's on the bottom, means smaller A, right? Like if I put a 2 here on the bottom, and I put a 10 there, right? Like 1/2 and 1/10, which one's smaller? 1/2 or 1/10? 1/10. So bigger number on the bottom, smaller value, kind of thing. Okay? And I think most people get that. They don't sort of understand the math of it. Okay, so if a force applied to a body rests, the body will begin to move, right? If there's no friction and I push on the book, it moves. If the body's moving in a straight line and a force is applied in the direction of motion, the body will accelerate. If the book's already moving towards Dylan and I give it another push, it's just going to go towards Dylan. And if the force is applied in a direction not in line with the motion, the acceleration will be in the direction of the force. Of all those, this is the most important. The acceleration is always in the direction of the force. If I drop the book, which way is the acceleration? Due to gravity. So which way does it go? Oh, sorry, which way is the force due to gravity? Down. Gee, it goes down. If I throw the pen at Dylan in the air, right, I force it up like this, I'm not going to throw it at you. Right? Which way is it accelerate? In the same direction that I push it. Yeah. The acceleration is in the direction of the force. Now, force we already know is a, starts with a V, vector. Acceleration, also a vector, right? Also a vector. And in fact, what does this proportional thing look like? Where do you think that comes from?
That.
Comes from that. Comes from that. You're not writing all that down, right?
No.
Okay, good. So if I rework that proportionality statement, I get the equation F equals ma. You've used that before in grade 10, right? F equals ma?
No.
What are they teaching up in Swan over there?
Probably not much.
F equals ma. What does the F stand for? Force. M stands for mass. A stands for acceleration. Now, the units. F is measured in newtons. How come? Newton. Newton was a smart guy. Letter N. Kilograms are measured in? Sorry. Mass is measured in kilograms. Kg. And acceleration is measured in meters per second or meters per second squared. You should know that 1,000 grams is a kilogram. And that 1 newton, because mass and acceleration are kilograms and meters per second squared, 1 newton is technically 1 kilogram meter per second squared. A kilogram times a meter per second squared is a newton. How much is a newton? Like, how much push do you need for a newton? Like, is that a lot? Is that, because if I come over there and give you a 1 newton push, would it hurt?
No.
That's about a newton. Empty coffee cup. Not a lot of force. 1 newton's not much. Okay, not much. If I push with a newton, it means that I can give a 1 kilogram mass and acceleration of 1 meter per second squared. Okay? So yeah, combining the units for mass and acceleration, we come up with the units for force. Kilogram meter per second squared, it's defined as 1 newton. Defined. Ooh, 1 more page to go. Newton's third law of motion. Now, I always get an argument here. When one body exerts a force on another, the second body exerts on the first a force of equal magnitude. Was this yours, Emily? Can you read what yours says? From the just. Yeah, does it just say equal and opposite reaction, or does it say reaction force? Okay, yeah. It really should say force. When one body exerts a force on another, the second body exerts on the first a force of equal magnitude in the opposite direction. Okay, Nick and I have a little disagreement, and I give him a push with 100 newtons.
Well,
Don't worry, I won't do it. What happens to my, do I feel 100 newtons back on me? I don't? Newton just said equal, if I push anyone with 100 newtons, he's going to push on back to me with 100 newtons, right? How come I don't go flying through the wall and he does? Oh, I knew someone was going to say that. I'm more massive than Nick right now. Probably because I braced myself and I've got friction there and he's not ready for it, right? Because he hasn't got his friction ready yet, right? But if he and I were on roller blades, I almost said roller skate there, like in 70s, right? And we sort of went like this, right? We each push, right? Equal and opposite, we both go back, sort of same thing. right? Okay. This occurs all time in nature. There is always an action and a reaction force. Always. Before I take my hand and I'm doing like, kung fu or something, and I smack that board. Yeah. Does my hand hurt? Yeah, it hurts. The board smacked me. It hurts. Okay? What about just a book lying on a table? Here I got my physics textbook sitting on the table. Is gravity pulling on the book? Gravity's pulling the book down, right? Because if I didn't have it on the table, it would drop. Put it on the table. Gravity's pulling down on it. There's a force on the book. Is the book moving? There's got to be a force up, right? The table is pushing on the book. The table is pushing on the book.
Push up.
The table's pushing upward. Have you been looking for this, JC? This new volleyball? It's been around a little bit, right?
Yeah,
Yeah.
I'm looking for that.
Yeah? If I push down on this really old volleyball, what does it look like underneath there? Looks flat, doesn't it? What about the top? I'm pushing on the top. Does it flatten it out? If the bottom's flattening out, that means there has to be I'm pushing on the top, right? Pushing on the top. It's flattening out. There's a force. Is there not a force there? I had one student a couple years ago, he didn't, right to grade 12, wouldn't believe that there was a force in the bottom. There is. Equal and opposite. Okay? We would call this one here, this is the weight force. This force here, I'd like you to label Fn. Normal force. And it's got nothing to do with it being normal. Normal is the fancy word for perpendicular. Normal force. Okay? All right, so that's sort of my little spiel with Newton's laws. Many of you yesterday got this handout. I'm going to wager a guess that no one's done. Anybody done this? And don't put your hand up if you are. Anyone done this?
I have like one left because I don't know what it is.
Okay. I'm going to give you the remainder of the time to work on this. Many of you probably didn't start it because you were working on other stuff. What time are we done here? 17, right? So we got a few minutes. If you want, anyone here left to finish writing their test? Just you, Brian, right? Okay, so, and you need two in? Okay, so let's get you guys finishing that. I'm going to try and finish up the marking. You guys can work on these. Tomorrow I'm going to go through the test, so make sure you're here tomorrow. Big day tomorrow.